Cool. So what last time before our Quizlet, we had finished up with the harmonic oscillator, and we were talking about like we got the energy, and then we were looking at wave functions. And today we're going to talk a little bit more about the harmonic oscillator, but we're going to go into a brand new system, the rigid rotor. Woo! I know, super exciting. So let's talk about the harmonic oscillator and reduced mass. So if you remember back in lab when we were looking at like frequencies, we didn't use mass, we used reduced mass. And we're going to talk about how we're going to move from a single particle harmonic oscillator like we've been doing and get to one where we have two atoms in there. So like we were looking at nitrogen or diatomic oxygen and so forth. So some harmonic oscillators are not a single particle. That's just moving back and forth. We're going to consider a diatomic atom or a diatomic molecule, excuse me, that has two different masses, mass 1 and mass 2. So consider a diatomic molecule with two masses, m sub 1 and m sub 2. And what we're going to assume is one is larger than the other. So if M1 is less than M2, we're going to try to draw that out. We're going to have M1 here. We're going to have M2 there. I probably should have drawn them a little bit bigger. There we go. That's M2. And let's say there's a bond between them. Okay, and we have to try and find the center of mass for this system. Where is it going to be?
Isn't it the mass is multiplied divided by the radius?
Oh, well, there's equations for every single different shape is the issue. So
Right.
like for this system, it'll be at the center of that bond-ish, but it will be offset due to the masses difference.
Right. So normally it would be right here if the two masses are equal to one another, right? Where's it going to be if M2 is a little bit heavier?
More towards M2.
Yeah, more towards M2. So it's going to be somewhere over here. We'll say this is our center of mass. This is x sub 2, so the distance between where that center of mass is and M2 is. We have x sub 1, which is the distance between where mass 1 is and the center of mass. Okay, everybody with me? All right. And if it's a pure vibration, meaning it's like an ideal vibration, the center of mass doesn't change. So even as these guys move a little bit, the center of mass doesn't change. In a pure harmonic oscillation, the center of mass does not change. So if we look at the change, we have m1 times dx sub 1 dt. So at some point, this mass, it's going to move a little bit over some period of time. That should be equal to negative m2 dx sub 2 dt. Okay, now we're going to do something a little weird, and it will make sense eventually. It might not make sense immediately. But what we're going to do is we're going to add m2 dx sub 1 dt to both sides. And it will make sense in a minute, but let's just see what happens. Okay, so we have m sub 1 dx1 dt plus that term that we just introduced. x1 dt. And then we have our other side where we have negative m2 dx2 dt plus m2 dx1 dt. How can we simplify this side? What can we do?
Pull the m's out.
Yep, pull the m's out. So we get m1 plus m2 dx sub 1 dt. What about on this side?
0.
Nope, not 0.
We can pull out the M2s.
Yep, we can pull out the m2s because if you look, that's a dx sub 2. This is a dx sub 1. Maddie, you're right. If these were the same, bam, 0. Like
I wrote it down wrong.
so, let's take out m2. Get dx sub 1 dt. What else do we get?
A negative.
Yep. dx sub 2 dt. Okay. How does this help us? Well, we're going to rearrange this guy. So rearrange to dx sub 1 dt m2 m plus 1 m2 dx sub 1 dt minus dx sub 2 dt. Okay, so now we have a relationship between these guys. Whoops, that's meant to be a D. Now we have a relationship between the change that these lengths are going through and the masses. But it's often more convenient to represent this, these coordinates as relative coordinates rather than absolute coordinates. So these are some points in space, but if we set a different arbitrary point, we can make our lives a bit easier. So it is more convenient butcher that word. And nope, was he an E? Better? Yeah, we'll go with it.
Where's Josh at? Just need his spelling expertise.
Oh,
Yeah.
I think you added an extra N in there. Like that EN doesn't need to be there.
Oh, okay.
Convenient. No, I think that
Convenient.
Right.
convenient. That says convenient.
Caveat. Yes.
You know
All
what I
right.
mean.
It's
Try again. How many
C-O-N-V-I-E-N.
chemists does it take
You
to
had it
spell
right.
a word?
Yeah, about that word.
V-E-N. V-E-N.
Yeah.
Convenient.
And you
I-E-N-T.
everyone's gonna judge us.
Convenient, right?
Yes.
That looks so wrong.
I
Convenient.
think I'm getting stupider without school.
I think so. Now that we're all
Can't handle a
online,
lot more of this.
I can blame it's all on Zoom that I don't know how to spell.
It's a Zoom glitch.
Yeah, it's the camera. It's not you. It's definitely.
Yeah, exactly. It's just how I look chubbier because of the camera too. That's that's why my hair looks crappy too. I blame that.
The mullet.
Not my mullet growing competition. It's all that. So, so it's easier to define this in terms of relative coordinates rather than absolute. Okay, so what do we mean by that? So what we mean by absolute versus relative is like, let's say we're looking at two numbers. The difference between 5 and 10. So if we subtract those two values, what are we going to get?
-5. I don't know which way you're doing
Yeah,
it.
-5. Let's do a 10 minus 5.
5.
So we get 5.
It's my favorite number.
Okay. Is
That's why I
5?
picked
Very
it.
good. What about the difference between 120 and 125?
Still
5.
Yeah, it's still 5. So in this case, the absolute coordinates are different. But what about the relative coordinates?
They're the same.
Yep. But relative coordinates are the same. Okay, so we're going to define one simple relative coordinate. We're going to call it Q. So we define the relative coordinate Q. And first question I have is this Q pointing the right way?
Yeah.
Yes.
Okay, we're good. Okay.
Not what I was expecting you to say.
Like, I feel like I can do D's better now.
That's good.
We're getting there. So we're going to define Q as the difference between 1 and 2. We know that the length 1 should be longer than length 2 based upon the system we set up when we said that the mass of 1 was larger than the mass of object number 2. Okay, so therefore, what's dq dt going to be equal to?
The change of,
Mm-hmm.
it would be delta x
Mm-hmm.
over
Sub what?
x of
Yep, x sub 1. And what's in the bottom?
DT?
Yep.
time minus delta x2 minus time.
Perfect. Yep. Okay, now we can sub this back into this equation up here. And this whole term is going to change. So sub this into our previous equation. And have you guys ever seen like dx sub 1 dt represented like x dot sub 1 like that? Geez, you can see it.
I remember being introduced, but I don't remember what it means.
Have you ever seen it like that before?
Just
I
lazy
don't think so.
notation, really.
Okay. So this is just another form of notation. It makes it way easier so we don't have to write DTs everywhere. They commonly use it in physics a lot, so that way it just makes your life easier. So we could represent that previous equation, we could have represented it as dx sub 1 or dx sub 2. We chose dx sub 1. But that's going to be equal to m2 over m1 plus m2 dq dt. Where again, this guy, that's used to indicate, that dot is used to indicate a derivative with respect to time. Used to indicate the time derivative. Of x. Okay. Now, if we choose to do it the other way, we choose to look at x sub 2, the change in x sub 2. So if we went back to the original part and if we chose to add m sub 1 dx sub 2 dt, instead you get x sub 2 hat is equal to m1 plus m2 dq dt. So it's almost the same thing as our previous equation, except if you look, we got m2 up top, and here we have m1 up top. Okay, we're almost there. So now, let's return to the Hamiltonian of our system.
Can you scooch it up a little bit?
Yep.
That other way. Yeah.
Other way? That work?
Yes, please.
Cool. Of our system. Let's look at the potential energy operator. So this is going to be the same. But the value of K, the kinetic energy operator, will change. Oh, I'm sorry, not the kinetic energy operator, just the spring constant. Okay. So we can get this spring constant. It's equal to 1/2 m1 x dot squared plus 1/2 m2 x dot squared. And where am I pulling this equation from? Where is it coming from?
Is that the spring constant thing?
Yep,
It's just classical.
Yep, it's going from classical physics. It's just that spring. Okay, and now we have expressions for both of these guys.
I hate this dot.
So let's sub in what we have, and let's try to simplify this expression. So we have an expression for that guy and an expression for that guy. So we get 1/2 m sub 1. What's this going to become? That x sub 1.
Is that dx1 over dt?
Yep, that is true. And then we found another expression for that. So what was that expression?
m1 over
Mhm.
m1 plus m2 dq dt.
Yep.
Fire.
Okay. And all of that junk is squared. And then we have 1/2 m2. What's it going to be in this bracket?
M2 on top versus.
Yep. M2 up top. Okay, cool.
So when that thing's squared, That doesn't automatically mean to take the second derivative, correct? It just
No,
means
it
that we're
doesn't.
squaring the value.
Right.
So did I write it wrong then for above?
Mhm.
If you put the paper up, did I write it wrong or did we write it wrong there?
Up
That one.
here.
That's
We
for
have
x2.
x2.
Oh, yeah, let's see. Oops, we wrote it wrong here. This should be a 2. That should be a 1, right? Oh, sorry, except that you can't
Oh,
see
yeah.
it. This should be a 2, and that should be a 1. My bad.
Good catch, doctor.
Anytime. That's what I'm here for. Doctors supporting doctors.
Yep. In this tough time, doctors got to represent.
Dr. Yule stopped class to congratulate me on the paper.
Oh, good.
I was like, autographs after class.
Well, when you get back to campus, we'll have a beer or something.
Maybe when I'm 30.
Maybe after the apocalypse.
Yeah. Publication beers are always the best beers. Okay, so now let's manipulate that stuff around. We're going to make this a little bit simpler. We're just going to aggregate this junk. So we get m1, m2 squared, 2m1 plus m2 squared. We're going to make our lives easy, just like we did x dot. We're going to do the same thing with q dot.
Should that be m2 squared?
Yep, that should be m2. There you go. What about the other term? What's that going to become?
Same thing, but m1 squared.
Yep.
Wait, what is this Q dot?
Q
Oh, wow.
dot is just equal.
Oh, it's a dq over dt.
Yep. We're just making our lives easy that way.
Is there another notation besides this dot? Because I keep thinking it's like a pen mark.
That's the common notation. Don't worry, we're not going to use it much. We're just going to use it in this thing and be done with it. We'll never see it again, to be honest.
Fancy X and Y.
Yeah. I just want to make people aware that that notation exists. If you go take a bunch of physics classes or math classes. Okay, and then what do we need down here?
2 times m1 plus m2.
Yep.
Okay.
Okay. Now, what we're going to do, we're going to try and slap stuff together and make this a bit simpler.
That has a q dot squared at the end, right?
Yep.
Yeah.
Q dot squared.
So can you just pull the Q dot squared out?
Mm-hmm.
Okay.
Also the bottoms, also one of the m's and one of the m1s and one of the m2s.
Oh, like along in here? Not quite, because remember, you got to
On
square this
top.
part first.
Well, yeah.
You can just do the top part plus the
They
other
can
one
they can be added
plus
together.
Q dot over
Yeah,
the
yeah, they can be added together. Just like you were saying, Maddie, they can be thrown together. And Josh, John, I think you were saying that too, right?
Yeah, I mean, you guys about simplifying, but that works too.
So let's do that. We're going to have m1, m2 squared plus m1 squared, m2 all over m1 plus m2 squared times q dot squared. Okay.
Why don't you just pull the bottom M1 plus M2 out squared?
This guy,
Yeah.
we'll see in a second.
Okay.
So now,
Alert.
okay. If we factor this guy, factor it. If we factor this, what can we pull out of here?
And m1 plus m2.
Yep. We get m1 plus m2. What else do we need?
And then M1, M2. M1 times M2.
M2 like that.
Plus. Oh,
Is it plus?
I think it's times.
Yep, should be a times.
Wait, what are we doing?
We're just pulling things out.
Yeah, we're just trying to make it simple, simpler. And I expanded the bottom for a reason.
because it cancels.
Yep. So what's going to cancel?
The M1 plus M2.
Yep. So that goes away. And what we're left over with is 1/2 M1, M2, all over M1 plus M2, Q dot squared. And now what this thing is, this is actually the reduced mass. We've given it the symbol mu. The reduced mass is defined as mu is defined as M1 plus M2. Oh, I'm sorry. M1 times M2 all over M1 plus M2. Okay, so now instead of having a lot of complicated junk like this, where we have to have multiple terms, multiple kinetic energies, we can use this reduced mass term, and we can just have one single expression for both of these systems.
What happened to the 1/2?
We're leaving it up there because we also have the Q hat up there.
Okay.
We're just gonna throw mu in there.
So this is equal to the potential of our system. Or actually, this is equal to the
Is that
I'm
K?
sorry.
Yeah.
Our kinetic energy. So therefore, instead
We
of
can't
having
see
two
that.
terms,
Can you lower it?
oh yeah, sorry. Instead of having two terms, we get one term, which simplifies our math a lot more and will make our Hamiltonian way easier to deal with in the future. K is equal to 1/2 reduced mass Q squared. Okay. And now, since we have a reduced mass, the benefit is this allows us to treat a two-particle system like a one-particle system. As a one-particle harmonic oscillator. Oops. Okay, so this benefits us in a way where previously we could look at a single atom, but then if we expand this to two atoms, we'd have to come up with a whole new Hamiltonian. We'd have to devise new wave functions, yada yada. But we have proved that we only need to look at the reduced mass to compare it to utilize our previous one-particle system. So we don't have to introduce a bunch of new complicated math. So as an example, the vibrational frequency of a one-particle harmonic oscillator, that nu is equal to 1 over tau which is equal to 1 over 2 pi square root of k over m. Where, do you remember what these things were? Like, what's this frequency? Yeah, this is frequency, but what's it the frequency of?
How many? The oscillation.
Yeah, the oscillation, basically the particle moving back and forth. This tau, what was that?
Isn't that like time?
Yep, it's the time. It's the time to complete a single
Period.
oscillation. Time to complete.
Look at these different colors.
I know, we're getting fancy. I missed my chalk, so I had to do something.
Yeah, you gotta.
Is your
Or-
pen like this?
Yeah. Or like those crazy pens that have like 4
Yeah.
different inks in them. The problem is I just continually snap them and annoy the living hell out of everybody near me.
Got the pens.
Yeah, like these clicky pens where you just.
Yes, it's
Yeah.
relaxing.
Are you
I
talking
had
about like
a
one of these
teacher-
things?
Yep. Yeah, one of those. They're great. I had a teacher
Have
that
self-control not to-
she would throw bananas. She was a Spanish teacher and she hated those things. And she would throw bananas at people if they were clicking them.
I have
Her
so many
name,
questions.
her name was Mrs. Barrera, and her father was actually a Spanish professor at Bonnet. And
Why does she have so many bananas?
she just would keep them in her office. So she's a
strapped.
really cool lady. I hated Spanish, and the way she got me to learn it was if she was like, "Here, grade everybody's papers." So it worked.
Teachers.
When she retired, she went to go teach in Ecuador, though, like for free. It was pretty cool. Random aside, sorry, we haven't had one of those in a while, right?
It's those
Yeah.
moments.
Any of these guys? What about this? What was that K?
Potential.
Spring constant.
Yep, spring constant. Yep. Not gonna work. Spring constant. Okay. So, yep, we remember all this stuff. Now let's say, what about for a 2 particle? A 2 particle. How is this expression going to change up here?
Would it be squared?
Nope, not
We
squared.
have 2 different times for the oscillations.
Right, so what you would have is you would have a 1 over, well, the oscillation we're talking about is like the spring just going. So that would stay the same. We'd have 1/2 pi square root K1 M1 plus
Aren't they the same springs? Would they have the same spring constant or no?
yeah, actually, that's a good point. So that's not quite true.
You just simplified all of pecan.
Yeah. We're going to simplify it.
There's
So
no
what's it going to
multipliers.
become? How's this
Is it
expression? gonna
M1,
change?
M2?
Nope, not M1, not M2. But what else?
Right, squared.
We still got a square root sign. We're going to go with a K. What happens to our mass?
This one.
It would be mu.
Yep. And just do a reduced mass.
Doctor.
Okay, cool. Good work. Now we're going to ask one more question. What does the Schrodinger equation look like for a 2 particle harmonic oscillator? Or a 2 particle harmonic oscillator. Do you guys remember the Schrodinger equation? What's the generic form of it?
H hat trident equals E trident.
Yep. H hat psi, E psi. Okay.
Yeah.
Now, what about,
I can't wait till you guys go to grad school and explain an equation like that.
yeah, say tridents.
Josh will probably be the only one that's going to use that again.
What you're telling me, how will you deal with the daily quantum mechanics you encounter in your regular life?
I mean, yeah, I know, right? I'll make it work. I'll make it work.
Josh, did you decide yet?
No, it's still working. on
Decide
that.
right now.
Josh,
Don't worry, you guys will be like the first to know.
month limit, like
Bars.
you anyway.
Okay, so how is this going to change? We know what it would have been in the past. Like, how did we define that Hamiltonian? What was it always in the past?
It splits up the kinetic and potential energy. So the K.
It was
Yeah.
K hat, V hat,
Yeah.
times that guy, right?
Yeah.
What was K hat?
The H bar squared over 2m, and it's negative, I think.
Yep, so it was 2m, right? What's it going to be in this case?
2 mu.
Yep, 2 mu. The x squared, because we're dealing with a one-dimensional harmonic oscillator. That potential energy operator. There you go. So that's all it's going to look like. All that ends up changing is we go from masses to mu, which is pretty awesome. We can now describe a more complicated system pretty easily, just like we've always done.
This is assuming a lot of things still.
It is. It works
Okay.
out pretty well though. So let's look at an example of this. Am I okay to move this up?
Yeah.
Okay. All right. So let's look at an example. The hydrogen molecule, so the H2 molecule vibrates at a frequency of about 1.32 times 10 to the 14th hertz. We want you to calculate the following things. A, the force constant of the HH bond. Oops, H bond. B, the change in energy. That accompanies a transition from the n is equal to 1 state to n is equal to 2 state vibrational level. And that's assuming the H2 atom behaves like an ideal harmonic oscillator. Behaves as an ideal harmonic oscillator. I'm gonna zoom out a little bit. Ah! All right, trying to help him. Okay. How are we doing on time?
2 minutes.
2 minutes?
Wait, mine's at 27 minutes.
Okay. Cool. All right, so we got to do some of these things. We have a H2, yada, yada. Let's start with A. What are we going to do? What are we looking for in A?
Okay.
Yep, we're looking for K. We're looking for that force constant. So how are we going to determine that?
Isn't it 1/2 mass times velocity squared?
That is acceleration. It's not quite that.
MA. F is equal to MA.
I think what you were thinking of was like that spring constant where you had K.
I don't know what I was thinking of.
What was it? Do we have any other ways we can do this?
Do we have to use the like generic equation for like describing the movement of the particles to find
We can
K?
try it.
That looks awful.
Yeah, it does look
So,
awful.
yeah.
Any
is
other
there
simplified equations that we know to get a spring
oh, it's
constant?
like m times 4 pi
Equals like
times v equals K.
What are you saying, Josh?
Isn't like F equals KX or like 1/2 KX squared or something like that?
Yep, so force is equal to what?
1/2 KX. Is that right?
We could, problem is we don't know force. We don't know this displacement at all. Any other things we can look at?
Seeing in our notes here that it could be equal to 4m times pi times v.
4m times pi. What's that? Where'd you get this from?
Previous notes, but it's derived from the like frequency equation technically,
Right.
and you just solve for K.
So let's go back to this, because the problem is we can't use m because m is for a single particle. So let's jump back to this guy. Okay, what are we solving for?
K.
Okay, so let's manipulate some stuff around. We get, well, let's move the 2 pi over, so we get 2 pi b is equal to square root K over mu. What else can we do here?
Square and divide by, or multiply by mu.
Yep. So
Wait,
4
so are we
pi.
finding the spring constant or the force constant?
We're finding the spring constant and force constant are the same thing in this case.
Oh,
Yeah.
Should have started with that.
If he
Is
said
equal-
that, we would have known.
Is equal to that guy, right? Okay, we can look these things up or we can calculate them. We have to get that reduced mass, but we have the rest of these things. We were told that frequency, we got pi, that's pretty easy. And 4 is there. Mu, what was mu equal to again? Something over something?
M1 times M2 over M1 plus M2.
Okay.
Yep. So if we do that, we have to look up the mass of, the resting mass of hydrogen atom. And it's 1.674 times 10 to the negative 27th kilograms. 0.674 times 10 to the minus 27 kilograms. Divided by 1.674 times 10 to the minus 27 kilograms plus that. Everything divides through, you get 8.370 times 10 to the minus 28. What are my units going to be?
Kilograms?
Yeah.
No.
Mhm.
Yep,
Do
you're
the
right.
kilogram square and then get rid of the kilogram square guy.
Yep, kilograms squared up top divided by kilograms in the bottom leaves us with kilograms. Okay, so now K is equal to 4 pi squared. We got those hertz. What did we say our frequency was again?
1.32 times 10 to the 14th.
1.32 times 10 to the 14th hertz.
Finish each
We gotta
other's.
square that. We got a reduced mass. That's also, nope, that's not squared, that's left alone. The value you get is 575. What are my units going to be?
Kilograms.
Mhm.
Frequency.
And then, yeah, hertz squared or
newtons.
kilograms per second squared, right? That's the same thing as a Newton per meter. Whatever way you want to express it. Okay. Now for B. We have to answer B. What are we doing in that part? When we said we're looking for the transition, the delta E.
Delta E. So we're doing the delta E equals like HC over lambda.
Yep.
Because
Yep. So what was E sub n? What were you saying, Josh?
well, so HC over lambda would give you lambda, which is a vibration, will give you a wavelength. But I remember for harmonic oscillators, it's parentheses 1/2 plus n times HV.
Yep. There we go. So now if we're looking at a difference between these two, what energy levels are we looking for?
1 and 2.
Yep. So E sub 2 minus E sub 1. So we got 2 plus 1/2 HV minus 1 plus 1/2 HV. What's that going to be? If we simplify that.
Just gonna be the 1, like,
Mhm.
yeah, it goes to just 1 plus 1/2 HV.
So let's
Not quite. Yeah.
right.
Or is it get rid of the half, so it's just HV.
Yep, it's just HV.
Yeah, okay.
Is that right? Let's see. We got 5 halves, 3 halves. Yep, we're good. Okay. So if we multiply everything through, we know H. What's the value of H again?
6.626 times 10 to the negative 34th joules times seconds.
Yep. And then we have our frequency, which was 1.32 times 10 to the 14th hertz. What's our final unit going to be in?
Joules.
Yep, I heard somebody whisper it.
Joules.
Yep, joules. We have 8.75 times 10 to the minus 20th joules for the difference between those. Okay, so your daily problem, I think, goes along with something along what we covered today, utilizing reduced masses. Are there any questions about anything we talked about today? No?